As we continue talking about electron configurations in atoms and putting electrons into the orbitals, I just wanted to spend a brief video talking about some of the exceptions that can happen for these electron configurations. These primarily happen with the transition metals, and it's not all of them. There's just a few exceptions here and there. And these exceptions are just in the order of which orbitals we fill first. And I don't expect you to memorize these exceptions. I often don't remember them myself, to be quite honest. But I do want you to understand why the exceptions happen, and if you were to see an electron configuration that is an exception, to be able to explain why it would be an exception and why it would choose to do that instead. So I don't expect you to memorize, oh, this one has an exception, this one has an exception. I won't ask you to do electron configurations for the elements that have exceptions, or if I do, I would take the normal way of doing it as the correct answer. But I do want you to, if I would tell you that an element has an exception, this is why it would have an exception. So let's look at a couple of examples to explain what we're talking about here. So the element we're going to look at here is chromium. So this is the atomic number of 24. And if we go over to our periodic table, chromium is right here, element number 24. And so its core electrons are going to be everything up to argon. So we're going to fill the, again, 1s, 2s, 2p, 3s, and 3p orbitals. And those are all going to be full. So just as a quick review, we could write the electron configuration for this as 1s2, 2s2, 2p6, 3s2, 3p6. And this is equivalent to, again, coming back to the periodic table here, this is equivalent to an argon core. So if we write this in condensed form, we would put argon here. And now the question is what happens with, we're going to fill in the 4s in 3d orbitals. And if we just kept filling it as we normally would, we would put 2 electrons in the 4s orbital and 1, 2, 3, 4 in the 3d orbital. So you might expect that this would be, I'll write this in white, 4s2, 3d4. But the actual electron configuration does not follow this. The actual electron configuration is 4s1, 3d5. So we still have the same number of electrons, of course, but for whatever reason, well, and actually we're going to get into the reason why this is an exception, we move one of the electrons from the s orbital into a d orbital. Now, why would this happen? Well, the total number of electrons we can fit in the 3d orbitals can fit up to 10 electrons. And there are a couple of arrangements of electrons that tend to have a slightly lower energy and are more favored. And those are half-filled orbitals, tend to be a little bit more energetically favored, and completely full orbitals. And the full orbitals are the reason why all of our noble gases don't react with other things. They're in a lower energy state. And a lot of what happens in chemistry is because everything else wants to be like those. We'll talk more about that in the next chapter. But this configuration, this exception here with chromium, where we have 5 electrons in d orbitals and 1 electron in s orbitals, that gives us half-filled orbitals for both the s electron. So our 4s electron has 1. And if we look at the d orbitals, we have 5 of them. The 3d5 gives us an exactly half-filled orbital. We have 1 electron in each orbital with everything pointed in one, either spin up or spin down. So that's the reason why this is an exception, is that it's more favorable to have that half-filled 3D subshell than to have our full 4s electrons. It's not obvious that that would be the case without doing measurements, but through measurements, we've been able to determine that this is what actually happens with the orbitals in chromium. Another example of an exception where the full orbitals come into play is as we go further along that same row in the periodic table, we'll look at copper. So copper is over here. It's our element number 29. So copper, I'm going to just use the since it's in the same row, it has the same core electrons, the argon core, and we would expect it to have 4s2 3d9, just based on its spot in the periodic table right here. So we fill in these 4s orbitals here, and we're almost full on the d orbitals. Zinc, they're all completely full, but we don't have it quite full in copper. So that's what you would expect based on the rules that we've talked about, but again, this is one of our exceptions, so that's not what actually happens. What actually happens is we fill the d orbitals instead of filling the s orbitals. So again, this is because full orbitals are energetically favored. Copper, it is apparently lower energy to fill that full set of d orbitals than to have that full s orbital. So one electron goes from the where we would have it in the 4s orbital into the d orbitals, and that is the ground state electron configuration. You can have this configuration, it's just not the lowest energy configuration. There are many other examples of this, particularly if you get down into the F block down at the bottom of the periodic table. Throughout these elements down here, there's lots of different deviations from the expected behavior, lots of exceptions. I don't expect you to know those exceptions, but I do expect you to understand what's going on, that generally these exceptions will lead to half-filled orbitals or to a set of full orbitals, a full subshell, like in copper, for example, here. All right, so that's our brief video on exceptions to our electron filling principles. In the next video, we'll start looking at some electron configurations for ions, what's happening with ions when we start losing or gaining electrons in atoms, and then also thinking about excited states. If we excite an electron, what do the configurations start to look like?